These are not real things. Let me say this out loud and crystal clear. Although AP Central may ask you to calculate how much flux is going through something, the term flux was invented to describe an idea that Faraday had. Oh gosh, we're still doing Faraday. Yes, we are. Faraday wanted to picture this thing he invented called an electric field. And it's problematical to do so. So what he did is he would take, let's see if I got a spot. I don't know if I have a spot for you to, oh yeah, I do. It's the very bottom of the front page. Go to the front page and flux lines. So what he did is he did this. He said, I've got positive 8 charge here. 8Q right here. I've got negative 4Q right here. And I'm going to move these down a little bit because I need a little more room because I didn't think this through properly. So right about here, make sense? I want to picture the electric field. So this is what he did because he's a genius and the rest of us don't understand stuff like this. He said, what if I say there's imaginary lines of force that are entering this object and leaving this object. Now, which one's going to create a greater field, the 8 charge or the 4 charge? 8 is. About how much more? 20. So it needs twice as many lines. We're almost done. You guys are waiting for me to do something genius. It's amazing how simple this next concept is. Got it? I got twice as many lines. Now, if I had 3 and 6, you could draw 4 and 8 if you want, if you feel better about 3 than 3 and 6, right? Because these charges can be 0.10305, whatever, right? As long as you get the scale correct, the drawing's valid, right? If this is 4 times as much, you need 4 times as many lines coming out of it. The lines leave the positive and enter the negative. Leave the positive and enter the negative. And I'll tell you what it does. So the next thing I do is I play with smooth curves, connect the lines. That's easy. A little harder. Now, once I've done all the connecting lines, especially not considering the outside, the rest of them just spread out as much as they can because they don't like each other. So what would that mean? This one's going to go straight that way. This one is straight come in this way, right? This one over here is going to kind of bend that way out. This one's going to kind of maybe head that way. Kind of same thing here, right? It's going to kind of bend out that way to stay equidistant between the lines. And then this one's going to kind of go maybe that way. Congratulations, you just done your first flux diagram. I did it. What does this do for me?
It tells you the field, what the field is.
If I put a charge right here, which way is it going to go? Well, flux line. If I put a charge right here, which way is it going to go? It's going to go that way. If I put it right here, what's it going to do? It's going to be pushed by this guy, but it'll be attracted by this guy, so it's going to probably travel on some sort of thing. If I do this correctly, it actually tells me which way the charges would go in my field. It does something else, which is actually slightly more important. And that is, the closer the lines are together, the stronger the force, the field, right? In this area, the field is very great. Over here, the field is very, very small. Over here, it'd be almost non-existent, right? If you're equal potential lines, way out here, this is the way he pictured an electric field. Now you're thinking, that doesn't have much use to what picturing electric field was. I'm telling you right now, this is the most important thing you're going to learn in the second semester, is what this is and how it works. It is a mathematical trick to get around really awful calculus. Okay? But I'm not going to teach you the whole trick this chapter. I'm going to teach you the rest of it next chapter. It's called Gauss's Law. Okay, it's Gauss' first mathematician to try to figure out what he was doing and make it into a real law. Okay? But here's Faraday's picture. So with that in mind, I want you to try on 11.7, number, nope, I lied, 11.8, number 1. 11.8, number 1. Try that out.
So, what's going on 4?
Okay, you chose 4. Now, could I chose 8?
Yeah.
I can. Just for the record. And by the way, you should be able to recognize what flux lines look like. They once in a blue moon ask you to sketch some, and they give you great latitude as to what you decide to do and don't decide to do. Okay, for the most part, it's just the idea that we really, really need to grasp right now. Okay, that this tells us what the field looks like. Okay, and it could tell us which way a charged particle would move, and how much acceleration it would have based on how close the lines are together. Right? Yeah. Okay. All right. So then, what do we do on this one?
Horizontal.
There, but there I go in. Yeah. And again, they have to be symmetric around the outside. All right, what do you got for me?
Those two attach.
Good.
I had big loops.
Good. Loop.
Yep.
Loop.
And chase.
And then going off to infinity and coming back in like an asteroid scale. Good. You'll see some diagrams will curve one of these up and the other one down, as you will. Again, if the idea is that. All right, number 2. What happens if I change them into pluses and move them closer together? Wait, let me go back? 4 plus. 4 plus. What do you got going on now? We got out. We got out. We got out. We got out, we got out, we got out, we got out, we got out. Connor?
Yeah.
The disposition of these lines is they don't like each other, right?
Absolutely.
So they're going to try to avoid each other. So how would that go?
Maybe wouldn't connect at all.
Wouldn't connect at all. In fact, they're going to try to veer almost instantly. Yeah, drop a smooth curve, but they're going to veer this way, right? These detecting more lines here are going to tend to drift that way. This is going to run straight for the other side of the root. This is going to drift that way. This one's going to eventually end up straight up and down, probably. This one will drift off the back side. This one will drift that way, and this one will run that way. Notice what it predicts. If I put a charged particle here, a positively charged particle in here, which would happen? If I put a negatively charged particle, it goes the opposite direction of the arrows, right? So it tend to drift inwards until it got caught by one of the two and then got pulled in. Right?
Is that ever a thing where,
Let Brandon finish his question.
if you put a negatively charged form on the bottom, it would go to one side, and on the top, it would go to the other side?
No, no, that's a fault of the diagram, right? You oftentimes see textbooks that are cowardly will do this on this diagram. They're like, oh, you should turn them in this case, right? And so what does that mean? So then I got a nice, easy, smooth, erp, 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 erp,
That's not
erp,
always what happens.
erp. Oh, sorry, erp, erp. But that's cowardly.
Yeah.
But it does create something interesting in the middle. There is a spot in the middle, which what happens?
We can just stick there.
Right? It would be a place where it's got equal and opposite forces, right? It'd be pulled both ways, but couldn't go either, right? Because it's got equal force. That would, both diagrams show that spot. There's a spot in the middle where there's actually no electric field. The desire to go one way is the same desire to go the other way. Which way you happen to be will determine which way you end up going. Make sense? Okay. Yes, sir.
So would this tell you the critical distance between, like,
If you are really, 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 really good at it, which none of us are going to get that good at it.
the computer?
But we're going to get really, really good at it in a different way. We're going to figure out a way to turn this into numbers that we can actually calculate. That's what we're going to do. All right.